briefly, but about conformal field theory. So let's just go quickly the basic background. So we'll do conformal field theory because it's sort of supposed to be a universal theory of second-order phase transitions, and also about quantum field theories in the limit of small or large scales. And the reason that's a good reason to study it. So it's representing universal classes of critical phenomena in statistical physics, but it also has very rich structures. It has a rich symmetry, and that allows for a lot of calculations, as everybody here knows. I suppose from every talk here, one gets the impression that it's sort of hard to come up with a rigorous definition of conformal field theories. So one possible approach to such a thing is to start with a probabilistic approach, and that's what we have been doing, and that's what this talk is about. But before I go into it, let's just fix notation. So first of all, in the probabilistic setting, we have random fields. These are what we're used to call in the previous lectures operators or fields or operators. So these are random fields, and we have some. We are interested in the correlation functions, where the bracket refers to expectation in some measure, not a probability measure necessarily, but and not even a positive measure necessarily, but the rate will be a positive measure. There will be correlation functions will have invariances in the conformal in this business. We are arguing that they have invariances under operations and translations, and also under scaling. And when you scale the points, the invariance is just a multiplicative factor, and there's a scaling exponent, which is usually called conformal weight. And the conformal field theory, the conformal symmetry extends this symmetry not from those operations to actually to conformal group, which in two dimensions is just very familiar Möbius maps, and this is probably everybody has seen these things. Now, the conformal symmetry determines 3-point functions in every dimension up to constants. The constants are called structure constants, CFT, and in the two-dimensional case, we can just put the points, for instance, on the plane to the 0, 1, and infinity. There's some numerical factor, and everything else about the 3-point function, the spatial dependence is fixed. Not so for higher point functions, but this bootstrap hypothesis, or operator product expansion, which has been discussed in Bertrand's lectures, for instance, a lot, is this axiom that you can iteratively determine these correlation functions. N-point function is related to n-1 point function with explicit coefficients. And the coefficients are completely determined by the structure constants and by the conformal symmetry. That's the operator product expansion hypothesis. So if that holds, then at least in principle, it looks like everything is determined in terms of 3-point functions and explicit factors. So that's the ultimate thing one wants about the conformal field theory, is to carry such a thing out. And as it was stressed by Bertrand, this is a very overdetermined thing. You can sort of get rid of these points sort of in various orders, and you should always get the same result. So you get lots of consistency conditions, and if you do it for the 4-point function, You can do it in basically two ways, and that consistency condition is already so constraining that in some cases it leads to, you can, based on that, guess solutions. So that's how this whole business started in 2 dimensions by Belyavin, Polyakov, and Zamolodchikov, who came up with such solutions in models like 2-dimensional easing model. Okay, so the question is, how do you come up with some sort of mathematical formulation of CFT where you could actually check the bootstrap hypothesis? So prove that it actually holds, and then implement it for a complete solution. Okay? So what we try to do is to study conformal field theories which are given by path integrals. Typically, quantum field theories, actually, the ones which one uses in physics are given by path integrals, namely, they come from sort of quantizing classical field theories, and classical field theories are described by action functionals. So, we are talking about Euclidean field theories, and you do path integral, something like that. So this correlation function in that formulation is given, these v's become some functionals of some underlying fields. So we have some fields defined on the underlying space, taking values in some other space. And these operators, or these random fields, are functionals of these underlying fields. There's an action functional depending on those fields, and you're integrating over formally over all field configurations, like a Gibbs factor. And then in such a setup, to look for conformal field theories, you should find some reasonable candidates what to put here in order to actually produce a conformal field theory, at least heuristically, and then to figure out whether you can actually make mathematical sense out of such a path integral. And then if you can even do that, then try to derive bootstrap from that. Okay? That's the sort of program. Any questions about just this basic?
And W and V, how are they related?
I'm sorry?
How is W related to V?
Depends on your theory. So in Liouville theories, e to the alpha times phi.
Ah, okay, that kind of thing.
Okay. Okay. So what are the examples? So let's start with classical conformal invariant field theories. So here the setup again. We have we are now in 2 dimensions. So our fields are functions from the 2-dimensional surface, 2-dimensional manifold, to some other manifold called, I will call it M. And so the sigma is a 2-dimensional surface equipped with a Riemannian metric. Okay. And then you have some action functional which depends on the field and the metric. And in that sort of framework, conformal invariance just means that this guy, first of all, is invariant under the action of diffeomorphisms of the surface, namely, if you move the fields and the metric, nothing happens. The action stays the same. But on top of that, conformal invariance means it's not only diffeomorphism, but it's also while invariant. Namely, if you multiply the metric by a positive function, it stays the same. In particular, that means that the action depends only on the complex structure determined by the metric. Okay? These 2 conditions here. And the simplest example you have seen, of course, is the free field, where the action is just, the target space is just real numbers, and the action is just the dilutionary energy, namely you take the absolute value squared of the gradient squared, so d phi squared, and integrate it over the Riemannian volume. And these two guys transform in the opposite manner under wide scalings. It's obviously diffeomorphism invariant under wide scalings, and this is wide invariant. And then you can, as you know, go to complex coordinates and write it in complex coordinates just as an integral of d phi and d bar phi. Okay, so that's a simple theory. And of course, classical theory is very classical. It's a story about harmonic functions, stuff like that. So the more interesting example is the nonlinear sigma model, where now the target is also, well, it's a Riemannian manifold also. So I denote its Riemannian metric by little m. So, so the field takes value in this Riemannian manifold, and the action function is just like in the free field. You take the derivative of this map and take its square. You have to think about what this means. I mean, the derivative of the map is a cotangent vector on the surface, and it's a tangent vector in the target space. Both these guys are equipped with their own metrics, so you can take the square, integrate it over the volume, and that's called nonlinear sigma model. So again, from the point of view of the sigma, you can go to complex coordinate. This is obviously wide invariant, and then you can write, if you write it in local coordinates on the target space, it looks something like that, like we had in the free field. So there's a dz of, you have some n-component field, and you take dz and dz bar, and then you have some non-linearity coming from the metric, which depends on the field. Okay, so this is a non-linear version of the linear theory of free field. Okay, again, it's sort of a classical story. It's an extrema of that object. There are harmonic maps between those two manifolds. The third example is Liouville, which we have seen many times already. Such a thing is in general not wide invariant because the volume gets multiplied by exponential of the phi factor, but nothing happens here. However, if you take exponential of the field phi, then you sort of when you first see it, it looks a bit miraculous, but you get actually conformal invariance in the following sense, namely, you just add a linear term with a particular coefficient to the action. So you put such a term and you add a linear term, where you take the scalar curvature and a number which in these units is 1 over b, where if the exponential is e to the 2b phi. And then, while the transformation of the metric is the same thing, can be undone by just a shift in the field phi and up to a constant, and the constant is called Weyl anomaly, and we saw it today in Guillaume's talk. Okay, so Liouville theory also has this sort of structure where it fits into this business. Okay, so there we have examples. So how do we define the path integral? Again, for free field, Remy already explained how that's defined. In the free field, this is just you do the obvious. You write the field as the Gaussian free field, and then it has a zero mode. So this path integral, you integrate over all the functions here. So you should view this as the function having two parts, a probabilistic part, namely the Gaussian free field, and then just a real number which you integrate over. So you integrate over the constant mode, you take average over the Gaussian free field, and we wanted to have unnormalized integrals, so we multiplied by the partition function of the Gaussian free field. So that's the definition of free field integral. And Gaussian free field, again, you have seen that that's a random Gaussian distribution whose covariance is the green function and the Laplacian on the surface. So that's what Remy explained yesterday. And the factor here, let's not pay too much attention to it. It's given by in terms of a regularized determinant of the Laplace. Questions of free field? Okay. And Liouville theory we saw also in Liouville. Well, in Liouville theory, renormalization is very simple. You just first of all, to try to make sense of it, you modify the free field, you convolve it with some approximate delta function, and then you renormalize it by defining it by multiplying by things blow up, but if you multiply it by things which go to zero, you end up having a well-defined limit of the exponential, and you should view the limit as a measure. That's the Gaussian multiplicative chaos measure. So that's how you define, and we use this notation for this multiplicative chaos measure, even though it's not absolutely continuous with respect to the body. Okay, so then the Liouville theory is defined as by a variation of the free field, where you have the free field here, and then you dress it up with whatever was in the action functional, namely the curvature term and this Liouville term, which was defined through the multiplicative chaos, and the rest is the same. Okay. And in this case, the primary fields, these fields which you are interested in, are just exponentials of the field. Again, you have to renormalize, but the renormalization is very simple. And as Remy, in the course of Remy and Guillaume, they tell you that the whole bootstrap actually holds for this theory. And it's a work of Colin and Remy and Vincent and François David and myself. Questions? So this is all about Liouville theory. But how about the sigma models? Now it's not the perturbation of the Gaussian free field. Remember, it was really very non-linear reaction functional. So how would you even start making sense out of it? Well, you should do the same as with the Liouville, that you regularize, you modify the field. You could even put it on the lattice or something, so that everything is nice. Then you're supposed to renormalize. In Liouville, we renormalized. We modified and multiplied the exponential by a power of epsilon. It was a very simple renormalization. Here, typically, it's much more complicated. And more importantly, even if you start with these conformally invariant action functionals, and you start doing this, there's no way you are going to get a conformal field theory. Okay? So, well-known example is the Heisenberg model. So you take the target space, now n-dimensional sphere, where dimension is at least 2. Then it's known how you should renormalize it. That was computed by Polyakov a long time ago. And you should renormalize it by just multiplying the action by a constant. 1 over temperature, as you could call it. And if you take this temperature constant to 0 when you remove the modification, it's called, this property is called asymptotic freedom. And it's believed that if you do that, you actually get a quantum field theory. However, there's a lot of evidence that the result is not going to be a conformal field theory, it's going to be a massive theory. Correlation functions will decay exponentially, don't have conformal scale invariance, no conformal invariance. And actually, everything, the same thing holds, or should hold, for any compact symmetric space, if you take the bucket. So this huge zoo of conformal invariant actions looks useless. Don't seem to get any conformal field theories. There are some esoteric cases which might give rise to conformal field theories. Let's not go to that. Okay, but who told you that that's the only term you can put to the action, namely this nonlinear sigma model? There's another dimension 2 thing, so having two derivatives that you can put in the action, namely pick a 2 form in the target. Okay? Target space. Then you can pull it back to your surface with this phi, and you can integrate that over the surface. Okay? Again, writing it in these local coordinates, it looks like this. So you have now a wedge d phi, and some antisymmetric matrix here, depending on the fields. That's obviously not only while invariant, but it's actually invariant. It doesn't depend on the metric. So this is a that's why it's usually called topological. So this should be a legitimate object to put into the action functional. And indeed, such terms enter in string theory a lot. And, but a very famous example of such term is when you take the target space a compact Lie group. Okay, for SU2, for instance, SUN. The sigma model, there's a natural, natural Riemannian metric on the Lie group, namely the left and right invariant metric, which is given by the Killing form in the tangent space. And if you just translate the definition of the sigma model in this case, that's what the action functional looks like of the sigma model. So the trace of a matrix, so you take a derivative of you have a field which takes value in matrices, you take its derivative, multiply by the inverse, that's a Lie algebra object, and take the trace of that and d bar. So if you had just the group U1, so then G would be e to the I phi. So this should get I squared times d phi, and you are back to the Gaussian free field. Okay. Well, but as soon as you are not the U1, but actually these ones here, the renormalization goes exactly as in the Heisenberg model. Namely, again, what you have to do is to multiply the action by this diverging constant, and it should produce you some sort of quantum field theory, but it's not going to be a conformal field theory. But there is a B term here, which, if you add it to this action, should give rise to a conformal field theory. The B theory looks like the following, B term. Let me just write it. The dB is this 3 form here. So you take this 3 form in the group, so G inverse dG wedge itself 3 times, and take a trace. Well, this actually is not an exact form, so it's not D of anything, but sort of the obstruction there is integer, so that once you do this properly, you can actually write this term such that e to the minus k times the topological action, if k is an integer, is a globally defined action. Okay? So this is the definition of Wess-Zumino-Witten model. Questions?
So I is included somewhere, right?
I is included, yeah, it's here. Here is an I.
So if A is not integer, we not conformally invariant. Is that the claim?
If I is not, if what?
K is not integer.
If k is not integer, then you have ambiguity, okay? So this guy, you don't have a globally defined object.
Okay.
So it forces k to be integer. So you can add this term, but only with a discrete case, okay? Okay, so then the conformal field theory should look, you should try to make sense out of a path integral which looks like this. So you have some observables which depend on the G on the surface. And you take the sigma model, the group, and take this topological term, which we just wrote down. And you integrate formally with the product of Hahn measures. And then you try to define this so that for k integer, this guy makes sense, and actually it's expected to give us CFT. It has a very, it should have a very rich symmetry. It's not only conformal field theory, but it has an extended symmetry, namely it has a current algebra symmetry, which was also discussed. And it's a very rich class of conformal field theories, actually, because most of the so-called rational conformal field theories can algebraically be obtained from this WZW model by varying the group and doing something else, which is called the coset construction. So there is a super rich story about this. If you read the yellow book, half of the book discusses that. The rigorous construction is of the path integral. Not that people didn't try. However, there's a related model which is also interesting, which I call, let's call it the GWZW model. Its origin goes back a long time ago to the coset construction, what I told you about. And later it led to conjecture, which was by Christoph Kavetz and by Witten, sort of independently or separately, that somehow the group G WZW correlation functions, which we don't know how to define, but we believe that we have a lot of knowledge about them nevertheless. It should be recovered from those of the WZW model where instead of taking it on the group, you take it on the homogeneous space G complexified divided by G. Namely, you evaluate the action on positive elements of the complexified group. So you take the WZW action and plug in a positive matrix instead of unitary matrix. Okay? Turns out to be a sigma model on this homogeneous space, and it turns out to be a conformal field theory, and it turns out to have a probabilistic formulation. Okay? So let's look at it a little bit more. So think about SU2, okay? The complexified SU2 is SL2C, so 2 by 2 complex matrices with a determinant 1. If I look at positive matrices, I can write them as G times G adjoint. Think about just matrix groups. G times G adjoint, that would be a positive matrix. And in the complexified group. And in fact, what you put here, you can multiply it by unitary matrix on the right without changing this guy. So this thing actually only depends on GC mod G, okay? So we could try to do the following. We could define the path integral for its sigma model taken values in this space, this homogeneous space, by doing this path integral here, integrating over positive matrices, again, whatever it means, okay? Where this measure here is supposed to be the invariant, GZ invariant measure on the homogeneous space. Now, this space actually is a contractible space, and it turns out that this 2 form actually is exact in this case. So the parameter k will not be quantized, so this will work for any k. And this path integral actually can be defined in terms of GMC. Okay? So that's the reason it's sort of nice. Yes?
Is it really a special case when GC is the punctured plane and G is S1? So C star mod S1, is it? Do you get UV if you do C star mod S1?
C star.
So not at the punctured plane, not S1.
No, because.
You get the R plus.
No, because no, you could just. I think you could just free field, you know. Okay, so far for the generalities. So let's just now look at it concretely, the SE2 case, which is actually pretty interesting in itself. So, so forget about now everything. Let's start with the group SE2. And we look at the complexified thing, which is SL2C. So every matrix in SL2C you can write uniquely as a unitary matrix and a matrix of upper triangular form with the real things on the diagonal. And since the determinant is 1, this has to be inverse of that. And it's up to your convention what to put here. So we put here, there's some complex number gamma here, and we normalize things so that there's e to the minus 5 there, but with just choosing certain coordinates. Well, now you can write down, you take the sigma model action, what we had, the trace G inverse DG, blah, 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 plug that in and do a little bit of calculation, end up with such action. Okay, pretty simple. So the phi part is just like free field, there's a 2, but from that. And the gamma part has also quadratic in the gamma, but it's coupled to the phi by exponential of minus 2 phi. That's what comes out when you do the calculation. But here you recognize that this is sigma model. You can read what metric corresponds to that. It's this metric. So you think you write gamma as gamma 1 and gamma 2, the real part and the imaginary part. So you are in R3 with these 3 coordinates, and you look at the metric which is d phi squared, so the phi, and then e to the 2 phi times d gamma 1 squared, d gamma 2 squared. That's a hyperbolic free space. And if you take that space and write the sigma model, you end up with this action. That action comes from here, so that's what we get from there. Now, the topological term, you can also write. I told you that it's actually exact, and once the dust settles, it's quite nice also. It looks more or less like a little bit like these terms, except it comes with a minus sign. One of the terms comes with a minus sign. And that cancels one of the terms, and the WZW model is very, very simple action. It's DZ, there's a misprint, so this would be DZ, not DZ bar. So the free field for phi, and then d bar gamma absolute value squared, and e to the minus 2 phi, and that's it, that's the action. And this is supposed to now give rise to the conformal field theory.
What happens if you take like more general surface instead of the plane?
More general surface.
Like here, I think it's the plane, right?
Ah, here I
Yeah.
wrote the plane, but that's what's irrelevant here. This is already surface. This algebra here doesn't really deal with the surface at all. The algebra is in the target. Puzzled? Yep. Right? Remember, I mean, you got the complex coordinates, and then you don't see very much of the surface anymore. In the action, in the
Yeah.
So gamma is another field? Like
gamma is another field. So we have two fields: one complex field, gamma, and one real field, phi. Okay. Phi is just has action just this, and then gamma part has, and they are coupled to each other by exponential minus 2 phi.
Is the meaning in terms of hyperbolic space of this?
Sorry?
In terms of hyperbolic geometry, is there some meaning of this action function?
Hyperbolic.
Like sigma model with values in the hyperbolic space?
Yeah, exactly. This here is the action of a sigma model taken values in the hyperbolic 3 space, which is just R3 with this metric. Okay? That's the hyperbolic 3 space. And but then if you add this topological term, which also is in the Wess-Zumino-Witten model, that also has a nice comes in such form, and the result, this is not anymore sigma model in the hyperbolic space. This is Wess-Zumino-Witten type of thing in hyperbolic space.
So if you want the theory to be conformal, do you have to include the topological term like in the WZW model again? Is the theory supposed to be conformal at the end of the day? And is it only the case if the topological term is included, or also if it's not included?
If the sigma model is conformally invariant.
The sigma model itself, without a topological term, is not. No.
Okay.
Things just get inverted from WZW, which the usual sigma model has ultra-wild stable fixed point at in the free field. This is the opposite. So this has infrared stable fixed point at the free field. And the conformal field theory is an ultra-wild stable fixed point. Which also, so the realization group flow is completely just the reverse of what it is for the usual. Okay, so that's what we want to now do. So we take this action functional on the surface. We have some observable which depends on these two fields. And then we want to do the path integral where you put at each point, you put the SL2C invariant measure on the hyperbolic space. You can work it out, and that's what it looks like, into the 2 phi d phi d squared gamma. That's the formal definition of the path integral, and we would now want to give a probabilistic interpretation of what this means. But the story should be the following. It should give rise to a CFT. I told you that K is not quantized, but it turns out that K has to be bigger than 2. Okay? We'll see it in a moment why. And then there's a central charge which depends on K, then. It's given by this number. So this was studied a lot in physics. It was called Euclidean ADS3 because this hyperbolic space, if you it's sort of a Euclidean version of ADS3. If you make a certain analytic continuation of that metric, you get ADS3 metric, and it is at the space in 3 dimensions. For that reason, it was sort of studied by many people. Also here, Silvan, any other, everybody else. It was then observed that it should have a very close relationship to Liouville CFT, admitting a map to it. We'll come back to that in a moment. And also, it's claimed to have connection to a different field of mathematics, namely the Lagrange correspondence.
Sorry, can you elaborate on the last comment a bit?
Eventually, yes, yeah. But let's define it first. Okay, so that's the action function. So seeing what was done with Liouville, it's sort of obvious how to try to proceed here. Certainly you should take the phi to be the free field, so the Gaussian free field and the constant, and integrate over all those. And if you look at the rest, if I fix phi, the rest is also Gaussian, right? I mean, this is a quadratic form in gamma. If you integrate by parts, there's an operator which just integrate one of the derivatives by parts, and there's a differential operator which depends on phi. Sometimes it's called in geometry Russian, but never mind the name. It's this simple looking differential operator. So you should sort of say now that, okay, phi is the free field, and conditionally on phi, gamma is also Gaussian, conditionally on phi. It's Gaussian with covariance inverse of this operator, which looks like the following. You invert the d bar operator, and you invert the guy in the middle here. So more or less should look like that, okay? Also, remember we should have unnormalized path integrals, so you should also take the total mass of this Gaussian, so that's determinant of determinant of this operator inverse. Okay, it's a complex thing, so it's usually it's 10 to the power half, but we have two real things so inverse. And that actually, in this case, is a very nice operator. I mean, the phi dependence is completely explicit. It's given by an explicit expression, namely if I vary this thing with phi, it's well known what the result is. There is a quadratic term, namely like in free field, and then there's a curvature term, like in Liouville we have seen. So if I have a nice smooth phi, then this regularized determinant has such a behavior, and you see what it would produce then is e to the with a plus sign, similar thing as we have for the free field. So here we had the action, there should be a K here in front of everything, and a minus sign, and here there's a plus sign, so it becomes K minus 2. So this term changes the K here, and then you get the average term. Questions? Okay. And now it's nice to have the Green's function not having these factors of K, so you rescale your field by this factor so that you get rid of the K minus 2 in front of the Laplacian, and then you give the following definition. So that's always a motivation for a definition, okay? So far it's been heuristic. So let's define now the path integral as follows, namely you take an observable depending on those two fields. It's a normalization, never mind about that. And you do the following, you integrate both the gamma and the phi have 0 mode, so you integrate over them. And then you take expected value in the Gaussian free field, conditional on the Gaussian free field, such a thing. So this is expected value in the gamma parameter, which has covariance depending on the Gaussian free field. And then you take expectation in the Gaussian free field. So conditionally on GFF, the gamma part is Gaussian with covariance which depends on phi. It's a random covariance. This you should interpret as a Gaussian multiplicative chaos measure. So that's how we ended up with the GNC here. The covariance of the gamma coordinate in the target space conditionally on the phi coordinate is a singular integral of the GNC measure. Okay, and then what you can do, what we showed that this, first of all, makes perfect sense and defines a CFT with a central charge, which I mentioned already, and in particular, these fields being the primary fields. Is the definition more or less clear what it is? Okay. Yep.
My understanding is in the CFT side, people can go from Liouville to H3. There is a relation between.
Yeah, I will come back to it. Yeah.
But this is also true between the probabilistic association that you can.
Yeah, that's what I was thinking.
Gamma would be log correlated, or
Sorry?
gamma as a field, is it log correlated?
Gamma actually, this actually is almost surely not singular.
Oh, okay.
Because GMC is nice. If you integrate, I mean, if you take coinciding points, U and V the same, you get 1 over U minus Z's absolute value squared. The Lebesgue measure of that would be infinite. But GMC is.
When you say primary field, is it with respect to some Kac-Moody algebra? Or?
These are conformal primaries. This will also be Kac-Moody, but I haven't talked to you at all about Kac-Moody. Okay.
Is the theory reflection positive?
This is not reflection positive. So this is a positive measure, which is not reflection positive, whereas the compact double disease model is complex measure, which is reflection positive.
Is it easy to see by looking at the action that it should be reflection positive?
Well, it's not completely trivial to see that it's not reflection positive. Just by looking at the action, you sort of feel that maybe it isn't, but it's not. and which means also that if you go to the quantum field theory, then it's not unitary. Okay, so then let's go to what was asked about the Liouville correspondence. So you take those primary fields, those fields in the H3 model, which there are conditions on the weights for which they are defined. Let me tell you what they are. But for the ones which both sides are defined, the H3 correlation functions are actually given in terms of Liouville correlation functions by a remarkable formula, namely, you have these two parameters, namely the J, where do I have? So there's the phi part which has a J here, and then there is the gamma part which has the mu parameter. So what happens is that, first of all, the J part goes to Liouville. You put just a Liouville vertex operator at each point, where the alpha is related to this J by this following formula. So the J plus 1, this is basically what you would have if you just look at the previous. There was a J plus 1 here, and the B comes when you remember you had to put the B here. Okay, so that's not so surprising. The first thing here, this thing is just what if you just carry it on the phi, but then it gets you add to it 1 over b, but then you create a number of insertions at some new points y, where you put the Liouville field with minus 1 over b. So this is a degenerate Liouville field, and you put them in n minus 2 points. So such a is multiplied by an explicit function. So such a relation was derived by Bo and Teschner in 2000, at the beginning of this millennium. And now I wrote this to you, this relation when we are on the sphere on CP1. But you can actually do it on the surfaces of all genera. And you can also do it on a twisted version of the model, which means that you take these fields, which are defined on the Riemann surface, to have twists when you go around non-contractible loops. And the way to do that is that you couple the thing to a gauge field. And you get similar formula. We can, in the most general case, couple to arbitrary smooth gauge field, and the surface you get a formula which looks slightly more. These numbers change here. The number of degenerate insertions depends on the genus of the surface and the properties of the bundle, determined by the gauge field.
The YJ that depend on Z and mu.
I'm sorry?
The point Y.
Yeah, the Y, yeah, I should stress. So what are the Ys? The Ys are very complicated objects. They are functions of the Z's and the mu's here. It's a very amazing thing. Okay, so as I said, Sylvan and Teschner did this originally on the sphere. It was later by the Hikida and Shomeros in higher genus surface, also twisted with abelian gauge fields. but actually the whole thing goes through with non-abelian.
So the Liouville coupling is related to B?
Yeah.
It's 2B. Okay.
Before I give you, I should 3 minutes. Let me just, because you asked about the Langland, so this have sort of nice geometric interpretations here. So I told you that the classical limit, well, maybe I didn't tell you, but anyway, so let's look at a couple of limits here. I could take k to infinity. So remember, 1 over square root of k minus 2. Okay? So when k goes to infinity, b goes to 0, so that means that that's a classical limit of the Liouville. In that limit, if you look at, first of all, Liouville, you should look at the extrema of the Liouville action, and we know that they correspond. The Liouville equations basically say that the curvature of e to the 2b5 e to the 2b sigma times g has to be 2b5 times g has to be constant. That's the equation. So when you go along the while orbit of the space of metrics, the extremum is given by the constant negative curvature matrix. And then if you put these vertex operators, they create singularities in the metric, conical singularities in the metric. In the H3 action, there's a very similar thing, but it takes the action takes place not in the metric, but it takes you really have to define this action function of the field in the presence of a gauge field, and then if I won't write you the definitions, none of that, but there's an actual definition here, coupling to the gauge field, and then the extremizers are basically that well, G star, right? And then the extremizers are actually, you can think about this positive matrix as a metric on a rank 2 holomorphic bundle on the surface. And if you look at extrema of this action functional, the holomorphic bundle is determined by the gauge field. And the extrema are metric, in the extrema is conditioned that the curvature of the curvature of the metric connection has to be 0, so it's flat connections, unitary connection, so the one metric connection or unitary connection. And the vertex operators create now something which is called parabolic structures. So there's a nice geometric story on both sides.
And before you go further, the correspondence between Liouville and H3 you gave before, classically, do you have any simple interpretation, in particular the yj's that you had the new point?
This is something which should be very nice to figure out.
Okay.
This is more speculative, okay? So there's a semi-classical limit, which is called semi-classical or critical, depending on what point of view you take. Critical being that k goes to 2. Remember, k goes to 2, it goes to infinity, and b goes to infinity. So in Liouville it means b goes to infinity. In H3 it goes k goes to 2. And this limit has been argued to give in the limit. When you look at this path integral correspondence and take the semi-classical limit, critical limit. By Teschner and Gayotto and Teschner have argued this has something to do with the analytical analysis correspondence by these people here. Okay. But I'm sure there are people in the audience who know more about this than me. But this path integral correspondence, what we derive, has sometimes been called by Teschner quantum analytic Lagrange correspondence. I think I'd done my time. I didn't explain you the map to Liouville theory, so maybe just fix it. Know that there are many things to do here. The semi-classical and critical limits are interesting. Then, of course, the non-unitarity. Can you do Segal gluing in this case? There are cases of non-unitary. The imaginary Liouville is non-unitary theory where you can do Segal gluing. So that's something which should be interesting to look at. And then if you succeed doing Segal gluing, then the next step is to do bootstrap along the lines what Remy was explaining and Guillaume. Then, as been said in other talks, it should be also interesting to understand that other groups that listen to perhaps a map to Toda instead of Liouville. And then, of course, the original question we were interested in, which is still wide open, namely how to do compact WC. Maybe somebody comes up with nice probabilistic definition along such lines. Okay.